Now.
So, hello everybody to our Gamma seminar. Today we have the pleasure to guest Felipe López García from Universidad de Sao Paulo. We'll talk today about the reduction of cosymplectic groupoids by cosymplectic momentum maps. So, Daniel, thank you for accepting our invitation. It's a pleasure to have you here today. And the floor is yours, please. Thank you.
Okay. Good afternoon, everybody. Thank you, Professor Javier and Professor Xavier for the invitation to talk in your seminar. I'm glad to hear with you. Okay, today, as Professor Javier said, I'm going to talk about this work, reduction of cosymplectic groupoids by cosymplectic moment maps. This is a joint work with Professor Nicolás Martínez from Universidad Nacional de Colombia. Okay, the talk is divided in 4 parts. The first one is the introduction. I am going to try to give a motivation of using Lie groupoids and Lie algebroids in the context of symplectic geometry. The second part is a concrete definition of what is a cosymplectic groupoid and their infinitesimal data. The third part is about symmetries and reductions in the context of cosymplectic manifold and cosymplectic groupoids. And the last part is the main result in this work. So let me start with the introduction then. Well, as a motivation, I want to recall what is a symplectic realization. So for that, I'm going to consider a symplectic manifold E with symplectic form omega. You know, this is a closed, not degenerate 2 form. And also, I'm going to consider a Poisson manifold N with this Poisson bracket. For sure, in this symplectic form, I have a canonical Poisson structure given by the symplectic form. I mean, I can compute the Poisson between 2 smooth functions just by computing the symplectic form, evaluating in the Hamiltonian vector field. Well, a symplectic realization of this Poisson manifold N is just this map Q from E to M. It's a smooth map, which is also a surjective submersion. But also, this map is a Poisson map. In some sense, this preserves the Poisson structure between these manifolds. And I can codify this, for example, with this equation. The Poisson bracket on M is basically by taking the pullback with the function h, you take the pullback with q, you compute the bracket on E. Okay, always when you have a Poisson manifold, it's possible to obtain a symplectic realization. But if we impose a little more stronger condition, this is not possible anymore. So let me introduce this definition. What is a complete symplectic realization? So I start with this symplectic realization. Well, when I can consider a Hamiltonian vector field on the base on M, and well, this H is a smooth function on M. By compose with this Q, this is a smooth function on E. So I can consider this Hamiltonian vector field on E. So a symplectic realization is complete if for any complete Hamiltonian vector field on the base, this Hamiltonian vector field on E is complete again. Okay, and here appears this, which is, I think, is one of the most important theorem in this study of symplectic groupoids, which is this theorem by Marius Kreitnik and Rui Fernandez. So if I consider a Poisson manifold, this Poisson manifold admits a complete symplectic realization if and only if it is integrable. Okay, I'm going to explain what is integrable in this context, and this integrable is the motivation to the use of Lie groupoids and Lie algebroids. I can't see your face, so if you have any questions, you can ask any moment, because I am not...
Do not worry, we will do it.
For sure, for sure.
Indeed, I was about to ask what, in which sense is integrable, but after a while you said that you are going to explain it. So.
Yeah, just in a moment. Okay, let me. Well, now I'm going to talk about Lie groupoids, Lie algebroids, and okay, when I have a Lie groupoid, I can produce a Lie algebroid, and this is the Lie functor. In some sense, in some heuristical idea, is just take the derivative of this structure. So we can start with what is a top.
There is some problem with the.
Yeah, there is a problem. He has disappeared.
Yeah.
Okay, I will send an email and no. Hey, that.
Okay, what I'm saying is that okay, we have Lie groupoids, Lie algebroids, and a functor from Lie groupoid to Lie algebroid. That means that when you have a Lie groupoid, you can produce a Lie algebroid. So what is a Lie groupoid? This is well, you can think that this is consists in two sets: a set of objects, which I'm going to call M, and a set of arrows or morphisms, which I'm going to denote by G. And we have structural maps. For example, think an arrow in G, like this arrow, which objects y and x, and you have, for sure, you have this source and target map, which for any arrow, you obtain the source will be y, for example, and the target will be x. Okay. And also, this is a kind of generalization of the groups. So you also can think and you have a multiplication. But the difference with Lie groupoids, with the Lie groups, is your multiplication, it's possible, is your arrows are composable, like this two. You can multiply this one and you obtain this one. And this G2 is manifold, or well, the set of composable arrows, if you want. Also, you have this map. It's a map which going from M to G, and this is a generalization of the unit in the groups. So in this case, you don't have one unit, you have many units. For any point here, you produce a unit on the group point. That satisfies the algebraic condition that you want, and when you compose with a unit, you don't modify this arrow. And you have an inverse map, which for any arrow, you produce the inverse, such that when you compose these arrows, you produce a unit over a point. Okay, this is a topological definition, but if we impose a little more conditions, geometrical condition, we have what is a Lie groupoid. So a Lie groupoid, these G and M are smooth manifolds. All maps here are smooth, and S and T, the source and the target, are submersions. So on the other hand, the infinitesimal information of the infinitesimal counterpart is a Lie algebroid. And a Lie algebroid, you can think in this triple. This is a vector bundle A over M, an anchor map, which is a map of vector bundles from A to the tangent bundle. And you have a bracket on the section of this vector bundle A, which turn these sections in a Lie algebra. And also, well, this bracket satisfies this Line's rule, which combine the Lie bracket and the Poisson and the anchor map. Okay, this is what is a Lie algebra. Now I'm going to explain how you can produce from a Lie algebra one Lie algebra. Sorry, from a Lie groupoid, a Lie algebra. And I'm going to denote Lie of G, just in order to highlight that this is the functor Lie. Yeah. Okay. In the part of vector bundle, you will define this vector bundle. For sure, you have this map, source and target. If you take the derivative of this map, you have a map from the tangent of G to the tangent of N. When you consider the kernel of ds, you obtain a subbundle of dg. But you can, because you have this unit map, you can restrict this fiber bundle to M. And this is the definition of the fiber bundle of this case. And how you can define the sections? Okay, this is by doing this identification, as similar as in the case of Lie algebras. You can identify the section of A with the vector bundles on G such that they are tangent to the source fibers, the fibers given by G, vector bundles which are tangent to these S fibers, and also they are invariant by multiplication to the right, which is this equation here. Here I have the multiplication of the groupoid, and here I take the right multiplication, the derivative of this guy. So because we have this identification, we can consider this Lie bracket just by taking the restriction of the canonical bracket on vector fields, restrict to this this set here. And finally, the anchor map is just consider the derivative of the target map, restrict to A. And this is how you produce a Lie algebra. So now let me give you some examples. The first one, which is very natural, is think a Lie group. These Lie groupoids and Lie algebroids are generalization of this example. And how generalization in the sense that in a Lie group you have a unit. In the Lie groupoid you don't have a unit as just one element. You have a unit as manifold. So the idea here is that you can think your group of a groupoid over a point. For sure, when you consider the Lie functor, you obtain a Lie algebroid over a point, which is the same that a Lie algebra. Another example, which is very natural, is you can consider a smooth manifold, and you consider the unit a groupoid, which is for any object here, you define a unit here. Basically, you don't have multiplication over object here, you have only the unit over this object. And when you consider the Lie functor, you obtain this trivial bundle. Well, yeah, just by consider a zero section if you want. Another example, which is a little more interesting, is you can think in the pair groupoid. As manifold, you can think the Cartesian product between M's. The source and target are just the projection, the natural projection. And the product you can think in this formula here. You have these composable arrows because the source and target are the same. And the product is just consider the extreme values, X and C. And when you look the Lie functor of this guy, you obtain the tangent bundle. I mean, the anchor map in this case is the identity, and the bracket is just the bracket on vector fields. And now the example which motivate a little this integrable definition that I said before is this one. Let me consider a Poisson manifold M with this bracket. So I can define this algebra, this Lie algebra, as vector bundle. I'm going to consider the cotangent bundle. I can define the bracket and the Poisson, the anchor map in exact differential forms. It doesn't matter because I can define this locally and can extend this definition. So when you compute the bracket between two exact forms, is just by computing the Poisson bracket between the functions f and g. And the anchor map is just basically by consider the Hamiltonian vector.
Daniel?
So, yes?
Maybe there is a differential missing in the bracket?
No,
in the definition. Because it's a function.
Oh, yeah. Yeah, sure. It's missing, yeah, for sure.
Okay.
It's missing here the exterior derivative. Sure, sorry. You're right.
Never mind, it's just for clarity. Thank you.
Okay, thank you. So let me suppose that, this Lie groupoid G over M integrates this Lie algebra. That means that the functor Lie of G is this A. So it is possible to prove that there exists a symplectic form on G. And moreover, the target map will be a Poisson map, and also will be complete, because it's the similar case when you have an differential equation on a Lie group. You can extend the solution a little more and you obtain that your solutions are complete. It's very similar. So at the end, when you have an integration of this Lie algebroid, in the sense that there exists a Lie groupoid with information with Lie functor A, you obtain a complete symplectic realization. That means that integrable. But what I want to highlight here is that this omega also is a multiplicative form. I'm going to explain what is that. So multiplicative form is basically a differential K form in G, such that it satisfies this equation. You consider these projection maps from the composable arrows to the arrows, and the multiplication from here to here. And you can pull back by these three maps, and you have this relation. This is basically the definition of what is a multiplicative form. We can produce an infinitesimal version of this multiplicative form, which is called IM forms. So let me consider a multiplicative closed form alpha, K form. Then you can induce this IM-K form mu, which is a map from this algebra to the steric product of the cotangent. There is a canonical definition for that. You have, for example, you consider a vector on the algebroid. You take mu a, and you have to evaluate this in K-1 vector field, so vectors. What is the natural definition for that is, okay, you can compute this alpha. You need to input K vectors, and this is A x1 and xk-1. And in this part, it's important to note that I consider this inclusion, Tn in Tg and A in Tg. This inclusion is by the unit maps, and this inclusion is because these are basically the vector field which are tangent to the S fibers. And well, with this, just to close this part, with this definition of multiplicative form, let me come back here. I can intrinsically define what is a symplectic groupoid. This is a Lie groupoid, like this one, such that the arrow has a symplectic structure. That means that have a symplectic form here, which is multiplicative. In some sense, have this for on one hand you have the symplectic structure, and on the other hand you have that this structure is compatible with the structure of the groupoid. This was a kind of motivation in order to introduce these Lie groupoids and Lie algebroids to the world of symplectic manifolds. Now I'm going to do something similar, but from the point of view of cosymplectic manifolds. So let me start, or let me recall what is a cosymplectic manifold. This is this triple, a manifold G with a closed 2 for omega and one closed for eta. And if you suppose that the dimension of G is 2n plus 1, then this power omega to the power n wedge eta defines a volume form. This is a top form which vanish nowhere. So yes, to do the same, basically the same that we did for symplectic groupoids, I'm going to define what is a cosymplectic groupoid. So I start with a Lie groupoid G over M, and I'm going to consider multiplicative form omega eta, which are closed. This is a 2 form, this one is a 1 form, such that this triple is a cosymplectic manifold. It's a very natural definition if you think in the definition of symplectic groupoids. Okay, and what is the infinitesimal counterpart of this? Well, if you start with this cosymplectic groupoid, this omega induce an IM2 form. This is a map from A to the cotangent bundle. And I'm not going to explain very much this equation, this eta induce a one form. This is a map from A to R satisfying this equation. I'm not going to explain very much this equation. I just to mention that, okay, in this case, I start with a cosymplectic groupoid, and I can produce this form mu and nu such that they satisfy this equation. But I can think in a different way. I can start with a Lie groupoid with this form mu and nu satisfying this equation. And I can think if it is possible to integrate this triple. So I just want to mention that there is a characterization of this infinitesimal counterpart just by consider this mu and nu satisfying the equation 1, 2, and 3. Okay. Now I am going to draw a parallel between cosymplectic and Poisson manifold. This is a classical result, I think. On the left hand, I have cosymplectic manifold. Q with 2 for omega and 1 for eta. And on the other hand, you have you can define a Poisson structure on Q such that is regular. Well, you have the symplectic foliation, and if you have a cosymplectic manifold, the foliation have codimension 1. Every leaf of this symplectic foliation have codimension 1. And also here appears a vector field which is transverse to the leaf of the foliation. Basically, in a sketch of this correspondence is just by consider this. If you start with a cosymplectic manifold, you can produce this vector field just by consider the RIP vector field, which satisfies this equation, as classical, as usual. And if you start with a Poisson manifold, regular Poisson manifold of codimension 1 and this vector field, you can think, or you can produce your omega just by extending the direction. You have the Poisson bracket or the Poisson B vector defined on the symplectic leaf. You can take the inverse of this B vector on this, and you extend by 0 in the other direction, in an orthogonal direction if you want. And the canonical definition for this direction is by consider this transverse vector field. So the kernel of this omega is generated by this E. And eta is defined by the only differential equation satisfying this equation here. And okay, this maybe is just I don't know if this definition is correct, pre-cosymplectic manifold. You have this correspondence. But if you have cosymplectic manifold, I mean that omega and eta are close. If and only if the vector fields appearing here is a Poisson vector field. Okay, this is a classic correspondence in the world of cosymplectic manifold. But using that, it is possible to obtain this proposition. Well, this proposition is a little bigger. I just want to highlight this part. It's a proposition by Rui Fernandez, David Iglesias. If you have a cosymplectic groupoid, then you have a relation between the dimension of the arrows and the dimension of the base. In the case of symplectic groupoids, you have the dimension of G is equal to 2 times the dimension of M. In the case of cosymplectic groupoid, this version of cosymplectic, you have this relation. The dimension of G is 2 times the dimension of M plus 1. And I wanted to highlight this because I'm going to use this in order to produce some examples which are not cosymplectics. Until here, some question, or it's okay?
So far, it's okay.
I do have a quick question. I don't know if you can hear me.
Yes.
Okay. When you mentioned that the red vector field should be a Poisson vector field, does this mean that it is a symmetry or that it is Hamiltonian?
I don't know. When I say that this was a Poisson vector field, I mean that this vector field satisfies some kind of Leibniz rule. When you evaluate this vector field on the bracket of two functions, this satisfies some kind of Leibniz rule. This I mean by Poisson vector field.
Sorry, can you hear me?
Yes.
Yeah.
The Riemann vector field is an infinitesimal symmetry, the bivector in this case.
Yeah. Okay. Thank you.
Okay.
I think that is not Hamiltonian in general, but it's a guess.
Well, can I continue with, or it's okay?
Yes. Indeed, I think that if you write it in coordinates, cosymplectic study, you have a Dagout theorem, and the Poisson vector normally is defined in a 2n+1 manifold. And normally the partial of time is, let us say, is an additional variable. You have Q and P's, like the canonical variables is reflecting manifold, and the Riemann partial of T, and normally it does not belong to the image of the vector. It is normally the typical for symplectic in use. So normally it's a symmetry of the vector, but it's not Hamiltonian. But it's just as far as I remember. Because maybe I'm wrong.
Let me say an additional comment. It is not Hamiltonian because in a cosymplectic manifold is Poisson, and the symplectic foliation is just transverse to the vector field.
Yeah, that's the it's the same, but it is said in a better manner. I have to say.
Thank you.
Okay, so now let me consider a classic example of cosymplectic manifold. I can start with a symplectic manifold, G with symplectic form omega. Then when you consider this Cartesian product, for example, with the circle, you can produce here a cosymplectic structure just by taking the pullback of the symplectic form on G. This is the projection, the natural projection. And you can consider the projection, the pullback of this d theta, where theta are the coordinates of the circle. And this is a cosymplectic manifold. And in this case, the Poisson structure is just by consider, well, in the direction of G, you consider the inverse of the symplectic form, because in this direction it's not degenerate. And in the other direction, in the direction of the circle, you extend this by 0. With this example, I want to construct some examples of cosymplectic groupoids. So let me start with this symplectic groupoid. I mean, I have a symplectic structure here, which is multiplicative. And I want to do something similar to this one. So I want to multiply this by the circle. But I want to do that in some intelligent way, in some smart way, and just want addition the groupoid structure of the possibles in the circle. So for the circle, I have two natural groupoid structure. The first one, that I mentioned in one of the examples, is consider this like a group over a point. A structure of Lie group, you can consider this like a Lie groupoid. And the other possibility is to consider this just the unit groupoid of this manifold. So this is the first the G1, this first example, and the second one is by consider this structure. Both of these examples are Poisson groupoids. That means you have of co-rank 1. That means that they have a Poisson structure here of a regular co-rank 1. However, it is possible to prove that the first one is a cosymplectic groupoid, okay? But the second one is not more a cosymplectic groupoid, because if you look for the dimension of the arrows and you compare with the dimension of the bases, you have this equation, which is not the same that equation in the previous preposition. Okay. Now I'm going to pass to symmetries and reductions. Okay, to talk about symmetries, I want to consider this maybe classical case, if you want, or maybe this case that is a Lie group acting on the arrows and acting on ends. I mentioned that this is a classic, if you want, because we can think in a more general context. When you have a Lie groupoid, you can consider another groupoid acting on this guy, something like this. But I just want to consider a Lie group acting on arrows and this Lie group acting on the objects. I'm going to suppose that these actions are free and proper, both in G and M. So I can consider this quotient to be a smooth manifold. This quotient and this quotient are smooth manifold. Also, I am going to consider that these actions are compatible with the structural maps of this Lie groupoid. Whatever you think is compatible, this word for here is just by equivariant with the source and target map maybe are equivariant and so on. The idea when you ask for this compatibility is that when you consider this quotient, you again obtain a Lie groupoid structure, or yes, a Lie groupoid structure. I'm going to consider that this action is by cosymplectic diffeomorphisms. So this action will be also by Poisson diffeomorphisms on G. And if you have a cosymplectic structure on the object, you can push forward this structure to the base, to M, by taking, for example, the target map. And this action by cosymplectic diffeomorphisms on G will be a action by Poisson diffeomorphisms on G and in this Poisson structure on M. So at the end, with this consideration, I can consider a Poisson structure on G and a Poisson reduction on M, such that you have this commutative square. I mean, you have this Poisson structure and you can reduce this. It's a Poisson reduction. And here you have N and with the Poisson structure given by the push forward of the Poisson structure on the top, and you consider this reduction. And this map, the target map initial and the initial target map and the reduced target map, there are Poisson maps, and you have that these commutes. However, this reduction is not good enough in the sense of cosymplectic groupoids. Okay, what I said here is you start with a cosymplectic groupoid, you consider this like a Poisson manifold, and you obtain this Poisson manifold. But in the following example, I want to show that this is not more cosymplectic in general. And this is a very simple example. It's just by consider the previous example that I considered before. So consider this cosymplectic groupoid. Here I consider the symplectic structure of the canonical symplectic structure on Q, on the cotangent of Q. Here I consider the circle. And let me suppose that we have an action of the circle on Q, which is free. And for sure is also proper because this guy here is compact. So with this action, I can produce an action of S1 on this cotangent of Q times S1. How is the definition of this guy? It's just by consider just the action on the base, on the coordinates of Q. The direction of the covectors is still the same, it remains the same, and the coordinates of S1 is the same. You only modify the coordinates of Q. Let me suppose that this action preserves the cosymplectic structure. A very concrete example is you consider Q the plane without the origin. You can consider the action of the rotate, the rotation. So in this case, this preserves the cosymplectic structure, and by this consideration here, I can produce these reductions. And this guy inherits a Poisson structure. Okay, this is a Poisson groupoid. But what happened? If you compute the dimension of this guy, of the arrows, the dimension is, okay, in Q, you use one dimension because you have the action of the circle. In the direction of the covectors, you remain equal, being M. And I suppose that dimension of Q is M. And in the dimension of the circle is again 1. When you rearrange these numbers, you obtain this formula here, which says that the dimension of the arrows is the dimension of the base 2 times plus 2, which is different to the proposition that I mentioned before. For this reason, this guy is not possible to be a cosymplectic groupoid.
So, sorry, Daniel. In short, the thing you are doing is looking for a symmetry which will destroy the dimension of the final space, or this final space, yeah?
Exactly.
Because
exactly.
the same idea it works for many other things like contact or structure with a fixed dimension. Okay, thank you.
Exactly. You're welcome. Well, with this example, we see that Poisson groupoid, Poisson reduction is not good enough for work with cosymplectic groupoids. Instead, we can use an adaptation of the Martens-Weisstein theorem to cosymplectic manifolds. And let me recall what this theorem said. Okay, let me consider a Lie group acting on a cosymplectic manifold by cosymplectic morphisms. And let me suppose that we have this map from Q to the dual of the Lie algebra, which is a cosymplectic moment map. What that means? That means that this map is G-equivariant with respect to the coadjoint action on the dual of the Lie algebra. For any vector on the Lie algebra, when you consider this Hamiltonian vector field, because you have this map, you can pair this with an element of the Lie algebra, you can produce a function, a smooth function. So you can consider the Hamiltonian vector field. And the equation said, okay, this is equal to the fundamental vector field associated with this V. This is what is a cosymplectic moment map. It's very similar to the case of symplectic moment map. Also in this case, we have this condition for any vector in the Lie algebra. This function, when I pair the moment map with this V, is constant in the direction of the Reed vector field. Now, let me suppose that 0 is a regular value of J. In this case, this is a smooth manifold, and because we consider that this equivariance, I can restrict this action to the 0 level and is well defined. And let me suppose that this guy is free and proper. Okay. It is natural to think that this has a smooth manifold structure, just because this is free and proper, because you know the Godemont criterion. And the theorem says that also it is possible to endow this manifold with a cosymplectic structure. As natural, the definition coming from this diagram, you consider the 0 level here, you consider the inclusion, where Q have a cosymplectic structure, and from here to here, you consider the canonical projection, and this omega red and this eta red are defined by considering the pullback and comparing with the pullback of these guys. This is that's the equation. You consider this. You consider
Daniel,
this yes.
May I have some comments on this, on the theorem by Albert in general for this scheme? You know, just a curiosity first for you. Okay, we have here some people who have worked on cosymplectic reductions. So this is, for example, Manolo, yeah, De Leon. I don't remember if at the very end it was also Ruben. We have also myself. We have also Bartosz Iana. Yeah. So here there are several things I will tell you, just in case. We work for this, and for example, the condition that the moment mat is coadjoint invariant, what you said, it can be removed. Yeah, it's a little bit more tricky, but it can be done. Another thing is that, of course, the regular value of J can be restricted to some weak regular value. The action on the level set does not need to be free and proper. It's normally said that it's quotientable. Indeed, I don't know if Albert did it in this way. Okay, he didn't say that it is free and proper. He has said that we want the quotient space to be a manifold, a submersion, and said this is what we say that is quotientable, and that's the end of this story.
Yeah.
And a curiosity, the condition on the fact that the coordinates of the momentum map, they are integrals of the fundamental vector field of the action, the key. One referee said that it is too restrictive. Okay, once we finally managed. It can be done a little bit more general, but yes, as a comment, some people may think that this is too much restrictive to do it, for example, for physical example. So this is what I know about all this scheme. Yeah. So in the terminal parts, I think that it can be more general. For standard case, I suppose that for groupoids it will be the same. And some of these conditional sets, well, it can be a little bit more general. That's all. Thank you.
Yes, actually, there are some works of Enrique Bursin, for example, they don't mention that this is a, well, not in this case, but in the case of when you consider this reduction, they say that this is not a regular value, but they say a clean value, something like, okay, this is a manifold such that the tangent is okay, what you expect.
The kernel of the tangent space to the momentum map. Yeah, it's everything you want, everything, the minimum. Okay, yes.
Exactly, and this for sure, this free and proper is just for this to be a smooth manifold. But okay, if you suppose that this is a smooth manifold, okay, that's work. That's work.
Yes, another comment, because I think it was Albert, or I don't know if it's, I don't remember exactly, but there is some called ovifold. This is when the quotient is not anymore a manifold, but it's a fifth kind of stratification. And you could do something of the sort, okay? I think, more or less in 30 cases. But it could be nice to see if something like this can be done for group instead.
Interesting. Thank you. So now I'm going to, well, to finish this talk by talking about the result that we obtained here. So let me consider the infinitesimal geometric consideration that we do. So we start with a Lie algebroid with an in2 form and in1 form, mu and nu. And I suppose that this form satisfies the equation that I said before, the equation 1, 2, 3. So this is a different point of view. Instead of consider a Lie groupoid, I just consider the infinitesimal information, just the algebroid with this infinitesimal form satisfying this equation 1, 2, 3. So now I'm going to consider some symmetries at the infinitesimal level. This is an action of a Lie group on A by algebroid morphisms, covering an action of G on the base N. Again, I'm going to consider this action free and proper. So I also going to consider that mu is J variant. This J variant is with respect to the leaf of this action to the cotangent, and nu is J invariant. This is because mu is a map from A to the cotangent to N, and nu is a map from the algebroid to R. So in this case, it's just G invariant. So I can consider this canonical map from the cotangent of N to the dual of the Lie algebra. It's very canonical now. You consider here a covector, and you define this J canonical on the covector, evaluating in some vector of the Lie algebra, because you have a map here. So this is the only thing that you compare is alpha, which is an element from here, and you evaluate this in the fundamental vector field associated with this V. It's a very natural pairing. So you can define this map, a map from the algebroid A, which is by consider this in2 form mu, composed with this canonical map. And this map is also algebroid morphism if you think this like this algebra, and you can think this algebra like an algebroid over a point with trivial bracket. In this sense, this is a algebroid morphism. Again, as similar as in the previous case, let me suppose that this guy, the pre-image of 0 is a subbundle, a regular subbundle of A. It is possible to prove that this guy is also a inherit a subalgebroid structure of A. So at the end, because all of these considerations, maybe it's possible to be more flexible with these restrictions. Well, it is necessary that this guy is smooth. So you need that these guys are, reducible in some, as mentioned before. So you can consider this vector bundle, and this vector bundle inherit a Lie algebroid structure, and it is there is a possible to produce reduced IM forms, mu red from A red to this to the cotangent of this quotient, and this mu red, which is a map from here to here. And they are defined in a similar way as before. You have here the inclusion, and you have the projection, and they are defined in such way that when you take the pullback of these two maps, they are the same. They are equal on the level, on the 0 level. If you see, this is a kind of reduction in the infinitesimal level. It's very similar to the previous case. Now, let me now consider the global information, the integration. So let me suppose that we have an integration of the Lie algebroid. And I'm going to suppose that this guy is source simply connected. This is because I'm going to use this Lie theorem. So I'm going to consider this integration of A, and I'm going to suppose that these IM form are integrated by this omega and eta. That means that this mu and nu coming from the previous definition that I said before, when you have omega and eta. So from Lie theorem, you have that the action of G and A in A is integrated to an action of G of this Lie group in G by groupoid morphisms. Also, this action, this map, which is a morphism of algebroids coming from here to here, is integrated to a group morphisms of groupoids. Now I consider the groupoid structure here, the natural groupoid structure, which I start. And here the groupoid structure is this element as over a point, and the structure is given by the abelian structure here. I mean the sum in this vector field, in this vector space. And it is possible to prove that this map is a Jacobi variant, and moreover, it is a cosymplectic moment map. So what we can do is, by some consideration on the 0 level, we can consider this like a smooth manifold, this quotient, and here we can use the Marsden-Weinstein theorem for cosymplectic manifold and produce a cosymplectic structure on the arrows of this Lie groupoid. Yes?
I have a question. I mean, because in general, you can take, I mean, any level set of the momentum map. It doesn't have to be 0. Why are you taking 0?
The reason is because when you have this equivariant map, when you take the 0, you can restrict the action to this level. I mean, no, it's okay. Yeah, when you consider the 0 level, the equivariant says you that you can restrict the action of this Lie group, this Lie group, just to this level. When you consider another level, you can do some trick in order to say that, okay, this action is also well defined. But if you consider the zero level, this action and this is equivariant, this action is well defined in this zero level. It's okay? Or not so clear?
Yeah, I mean, it's clear, but zero is it's special case, right? I mean.
Yeah.
Okay.
You can try to generalize this as in the similar case of the Marsden-Weissan theorem for the symplectic case, and I suppose that for cosymplectic is also similar. Then you can consider another level set different from zero, but you have to impose some condition in order that this action is well defined. Okay.
Okay. Yeah. Thank you. I mean, it is well defined.
Okay. Okay. So I want to highlight again that because this guy is a manifold, just the zero level, because this is a regular value, and okay, because this is equivariant, the action is equivariant. No, the map is equivariant. Then this action is well defined on this level set. And if you suppose, well, this is important. If you start here with a free and proper action, there is a work of, I think, by Fernandez and Ratio that said, okay, if you start with a proper and free action here, when you leave or you integrate this action to an action of this Lie group on the Lie groupoid, this action also will be free and proper. For this reason, you can consider this equation as a smooth manifold, and that inherit these structural maps of groupoids, because these maps are by groupoid morphisms. And by using the Marsden-Weissan theorem for cosymplectic groupoids, you define some cosymplectic structure here. And also it's possible to prove that this omega red and this eta red will be multiplicative. In this sense, this is a cosymplectic group. Just for finish, I want to summarize this idea in this theorem. Well, you can start with a Lie algebroid, endowed with this IM24 and this IM14 mu and nu, satisfying the equation 1 through 3. So now let me suppose that there is a Lie group acting on A by algebroid morphisms, covering an action on the base on N. Let me suppose that both are free and proper. Let's suppose that mu is J-equivariant and nu is J-invariant. Then it is possible to reduce A to a Lie algebroid 8 red with this IM4 mu red and nu red. They also will satisfy this equation 1, 2, 3. And if there exists an integration of this Lie groupoid, I mean, you have this Lie groupoid with this cosymplectic groupoid, such that the Lie functor is this guy with this IM4 mu and nu. Then, when you consider the Lie functor of this reduction, the reduction that I mentioned before, you obtain exactly this the same. Let me explain that better in this diagram. Well, you can think in two ways. The first one is if you start with this Lie algebroid, with this infinitesimal information of IM forms, and you have some symmetry by the action of a Lie group, which satisfy this equation, this condition of to be free and proper, then you can consider the reduction. Well, also you have to mention here that the pre-image of this guy is a regular subbundle and so on. But the idea is that when you have this action, you can reduce it. But also, let me think now that you have an integration of this guy. I mean, you have a cosymplectic groupoid here, such that the Lie functor is this guy. And, well, the action here works in a well way. If this guy is a submanifold, then you can consider this reduction by using the classical Marsden-Weisand theorem. Then you have from here to here the reduction. And from here to here, you have the leaf functor. What this theorem said is, okay, all these reductions are well defined, and this square commutes. If you look for this and you look for this spot, this is basically the same. And that's all what I want to say today. Thank you.
So thank you, Daniel, for your talk. So is there any question, comment, remark?
I have one question.
Mm-hmm.
You mentioned, and this is known, right? Like when you have a cosymplectic manifold, the kernel of the eta defines the symplectic foliation of the induced Poisson structure, right?
Mm-hmm.
And
Mm-hmm.
usually when you do Poisson reduction by symmetries and you ask for the existence of the momentum map, you immediately have that really what you're doing is reduction on each symplectic reduction on each symplectic leaf, because because you're asking for the infinitesimal generators of the symmetry to be tangent to the symplectic leaves. So I was wondering whether these symplectic leaves have a very specific structure in the case of cosymplectic groupoids. I don't know.
Yeah, maybe one part of what you are saying is that you are asking that in the direction transversal to the regular foliation, you need that this will be 0. Okay, and in the case of cosymplectic groupoids, oh, this is maybe it's interesting. Maybe we obtain just a cosymplectic groupoid which is in some kind foliated by symplectic groupoids when you look for any leaf. Actually, there is a result by Rui Fernandez and David Iglesias that say, okay, maybe, well, this is a kind of this result. Actually, this is the correct answer is that, okay, you can consider the unit between G, between the leaf groupoid, and you can consider the symplectic leaf containing this this unit map, and they can prove that this leaf containing the unit is a well, actually, it's a symplectic subgroupoid of the cosymplectic groupoid. So what I am saying is, at least near to the units, you can consider this symplectic submanifold contained in your cosymplectic groupoid, such that it inherit some groupoid structure.
And
that's my sense.
Yeah, thank you. And do you know whether this cosymplectic reduction reduces to symplectic reduction on each of these leaves, or
No.
Okay. Thanks.
Okay.
So is there any other comment, remark, question?
Yeah, well, regarding my previous question about the 0 level of the momentum map, I mean, in the case of Lie groups, you get a well-defined Lie group action on the level set, not necessarily the 0 level set. So I believe that in your groupoid setting, you should get some subgroupoid on the level set of the momentum map.
Maybe it's possible.
Maybe I can say something about that. The election of the 0 level on the moment map of the Lie algebroid is indeed in order to integrate, because if you have another level different to 0, you cannot integrate to a groupoid. That's the reason you get, in the case of the group, you get a subgroupoid. It's the same here. You get the 0 level to to get a subgroupoid that will be the part of the quotient in the cosymplectic reduction on the groupoid level.
Okay.
Okay. Any other
Thank you,
question?
Nicolas.
So I will make a last question. Here you have made a reduction in the momentum map setting, but you always have the coisotropic standard reduction to make this kind of. So have you tried such an approach in this for these groupoids?
No, at the moment, no. This is a very recent work, so we have many questions now to to improve this article. Yeah, to ask. So this is just a future step.
Because it seems that it can be extended in many avenues. Yeah, there are many possibilities, and it's nice. I like it. Yeah.
Because, for example,
let me give
a
small comment here in the reduction. The way we think about this was by looking this multisymplectic reduction. There is a special kind of reduction in the multisymplectic case that it was by Casey Blaker, I think, that is when the multisymplectic form and the momentum map can be split. In this case, we have this three-plectic form, that is the two form and the one form in the cosymplectic case, and we can give an equivalence between the reduction that Daniel showed you and an equivalent to the split reduction in the multisymplectic case. That's the way we do it.
It did. I noticed because at the very beginning, when you defined the momentum map, it was very similar to the thing done in multiplicative geometry. Yeah, you have a point, you have the vector fields, and it's like the canonical form of getting the multiplicative.
And that's the reason we don't think about the coisotropic reduction or isotropic way, because we go directly to the multisymplectic case.
I see, and it could be quite tricky, I guess. Okay, it is the case here. I know that reduction that you have to assume very many technical things, and the multisymplectic structure, the case multisymplectic thing is something that we have in. I think that it was in one of the seminars of my department several years ago. So even you can go to see it here. Okay, I understand the point. Thank you. I noticed that, and I also noticed that the way of defining the bracket with the groupoid, it was like something. I was quite curious about the way of constructing, because you just gave it. You said that it must be its way, but I recognize some part of a Dorfman bracket and things like that. I was curious about how you did it. If you can give any of the detail about this bracket.
The bracket and the groupoid?
Yeah. At the beginning.
Let me come back.
Yeah, you go afterwards. It was a little bit afterwards. This is about Blaker. No. This was the Blaker, I think, and afterwards a little bit. How you define afterwards a little bit, please. This thing, yeah. The moment this is structure. This is what the previous one with the mu. Wait. This relation, yeah. How you did that? You can comment on it, because you said, I would say very.
Well, there is a word by Enrique that they define this in a very kind general definition. What is IMK form? And they basically satisfy that equation. This is
it works, yes. There is no more explanation about that.
Okay, I don't know. Nicolas, have some questions?
The way we can think this is that when you have the multiplicative form at the groupoid level, you have groupoid morphisms. When you take the leaf pointer to go down the groupoid morphisms from the multiplicative forms, you
Yeah.
get this formula at the Lie algebra. And this is why they get the formula in general, for general K form that are multiple, because they descend to a Lie algebraic morphism.
Oh, great. Okay, that explain it quite well. Thank you. Thank you. It's nice. Okay, and maybe a last question and we can finish, because I'm very curious, truly speaking, but maybe it's not the thing to have everyone here waiting. Because this is a cosymplectic groupoid, yeah, but the conditions of omega and eta, there are lots of other related structures. For example, omega is not closed, but it's, for example, a Lie4, I mean, the differential is, it can be written as a decomposable form between the eta or the omega or things of the sort. Have you, for example, like contact groupoid or something like that, have you think of that?
Oof, this is another word, but well, maybe this is a word for the future. But just to mention something, the last week, some guys here in São Paulo, they are working in this contact structure on groupoids and some kind of reductions. But this is a different techniques. Maybe it is possible to think in that from this perspective, but so it's something that we have to think for the future now.
Yeah, because in Albert, for example, as much as I remember, he does reductions, but he does reduction not only for the cosymplectic, he does also for the contact, and some results are just that you have omega, you have eta, and you can have a volume form. So it's things of this kind. And lately, I had some work, so I'm working on some things with generalization of this structure. And there is another thing with Albert is that he studies reduction that they are for cosymplectic to symplectic cases. So it's something that you have not been into here, but also it could be done. If you read Albert, we have a paper with Bartosz, with Adam, where some kind of relations cosymplectic to symplectic are analyzed. And they are more general than the Albert reduction. And it's something interesting you can think of also. Maybe I finish. I will not say anything more, but the work is interesting. And as I said, when I read it, I noticed that there are many possible avenues.
But then certainly we are going to read your work. It's very interesting because, okay, as I said, we just start now working on that, but we want to to produce more things.
Yeah,
if it's possible.
We will discuss with my colleagues also your work more deeply, because some questions were quite interesting. So thank you very much, and expect that we can talk. We will talk in the future. If we have any questions, we will let you know. So thank you. Please send me the slides. Okay, we will be very, very thankful. So that's all. This you can, Xavi, you can finish the recording.
Yeah, I just wanted to say that next week we will have Jorge Jover from the University of Zaragoza as our speaker. I will send the title and abstract in the next email to all of you. So thank you all for attending and see you all next week.
Yeah. Thank you, Daniel. Thank you, Nicolás.
Thank you
for everything.
Thank you.
Hasta luego.
Thank you.
Gracias por todo.